Hello everyone, welcome to the operating system series. So in continuation with the short-term scheduling algorithm, that is the CPU scheduling, we have already done two algorithms. The first one was FCFS, the second one was SJF, that was non-preemptive. Today we'll be doing the SJF, that is shortest job first, preemptive one. So let us first see the animation and then we'll solve one problem. So we'll start the animation. So on the left side we have the RAM and we have the CPU on the right side. So initially there is no process in the RAM, so process will arrive. So process P1 arrives in the RAM and the CPU bus is 8, and P2 also arrives and the CPU bus is 6. Now we start with these two processes. Let us assume now the execution begins with these two processes, and when the execution starts, we will have some more processes coming into the RAM. Okay. So now out of these two, P2 is having less CPU burst as compared to P1, so P2 will go for execution. So it goes for execution. Okay. Now because CPU bus is 6, so it now starts execution. CPU now will start executing the process P2 because it is of 6 millisecond, so it will start executing. And while this process P2 is in execution, P3 arrives in the RAM, okay, in the memory. Okay. Now as we can see, this remaining time of P2 is now 5. It was 6 now because CPU has begin the execution of P2. So from 6 it has come down to 5. Now 5 is remaining, but the new process which has come into the memory is of 4 millisecond. So if we compare, P3 is smaller, the P3 is smaller than the remaining time of P2, which is 5. Okay. So now because it is a preemptive SJF, so P2 will be preempted. Okay. So it will come out. Okay, this is preempted. Okay. And P3 goes for execution. Now P3 is remaining time is 4. Okay, it is of 4 millisecond. By the time P3 is executing, P4 arrives in the memory. Now P4 is of 3 millisecond and P3 is P3 was actually 4 millisecond, but because it was executed by the CPU for 1 millisecond. Now the situation is P4 is 3 millisecond which has arrived into the memory, and P3 is remaining time is 3 because both are same, so it will continue with P3 itself. So now P3 will execute 2, then as you can see, then 1. Okay, it is been executed by the CPU. So now this has been executed completely. Now P4 is the smallest of the 3, so P4 goes for execution. Okay. So now P4 is being executed by the CPU. So now 2, then it will become 1, and then P4 completes. Okay. Now after completion, we have 2 more processes, which out of which P2 is having less CPU burst. So P2 goes for execution. So it is from 5, then 4, okay, then 3, then 2, then it will become 1. So this is being executed. This is what we have the CPU burst time, which is decreased because the process is executed. Now finally we have P1, which has CPU burst as 8. Okay. So this process P1 will be executed finally by the CPU. Okay, when until it becomes 0, so that will complete the process. So this is how the preemptive SJF works. Okay. Now let us solve one problem based on this. So here we have this SJF preemptive scheduling definition. In this scheduling, the process with the least remaining CPU burst is executed first. Now let us see one example. So we have this set of processes. We have to find the average waiting time and average turnaround time. So we have process P1, CPU burst is 7 and arrival time is 0. Process P2, CPU burst is 6 and arrival time is 1. Process P3, CPU burst is 4 and arrival time is 2. And process P4, CPU burst is 5 and arrival time is 3. Now you must see that when arrival time is given as 0, it means that when we start the system, when we start the execution, only one process is available for execution, that is P1. After 1 millisecond, another process enters the system, that is P2, and after 1 more millisecond, that is after 2 millisecond, we have P3 in the queue, and after 1 more millisecond, that is 3 millisecond, we have P4 into the system. So when we start the system, only one process is available in any problem, if this arrival time is not given, it means that all the processes they are available for execution. But in this case, with arrival time, if it is 0, means this process P1 is available for execution when we start the system. So first of all, we'll draw the Gantt chart. Now this is the Gantt chart. So initially, as we can see, process P1 is available at arrival time. It is available when we start the system. So this goes for execution from 0 times 0. After 1 millisecond, okay, after 1 millisecond, what happens is this completes. This 6 is remaining, okay, 6 is remaining, and the new process, which is P2, it arrives in the system, but its CPU bus is 6, so both are same, so it will continue with P1 itself. So after 1 more millisecond, okay, new process P3, this P3 arrives in the system after 2 millisecond. Now the remaining time of P1 is actually 5, okay, this is 5, okay, and the new process which arrives in the system is 4. So this process is preempted, okay, so it is taken out, and P3 goes for execution, okay, from 2. Now because it is of 4 millisecond, okay, so 2 plus 4 is 6. Now after the execution of P3, what we are left is 3 processes. This is left. I'll just cancel out this. So we are left with 3 processes. P1 with 5, because 2 is already executed, so we have this P1 left is 5, and P2 is 6, and P4 is 5. Now because we have already started with P1 and this 5, and P4 is also 5, but we will start, because we already started P1, so we start with again with P1. So 5 is left, so 6 plus 5 is 11. Now this goes out. Then we have 2 processes, P2 and P4, but because P4 is smaller than P2, so P4 goes for execution. It is of 5 millisecond, so 11 plus 5 is 16, and finally, so this also completes, and finally we have P2, 16 plus 6, that is 22. So this is the Gantt chart. Now let us see the how do we calculate the waiting time. Okay, now we again draw this Gantt chart here. This is the Gantt chart. Okay, so first let us see for P1. Now P1, as we can see, the waiting time is actually 6, where P1 finally executes. So this is 6, but 2 millisecond has already been executed, so we need to subtract 6 minus 2, that is 4. So this is the 4 is the waiting time for P1. Now regarding P2, as we can see, P2 starts at this point, okay, this is 16, okay, but because the arrival time, okay, as you can see, the arrival time is 1, okay, so it means that it has arrived 1 millisecond late. So we need to subtract this 16 minus 1, so it is 15. As we can say 15, it is not 16, it is 15, because 1 millisecond was the arrival time, so we need to subtract the arrival time. Then with respect to P3, so P3 is here, it starts at 2, but as we can see, 2 is the arrival time, so we need to subtract this 2, so 2 minus 2 is 0, okay, so that's why we get this as 0. Okay, similarly for P4 it is here 11, okay, but 11, the arrival time is 3, so we need to subtract 11 minus 3, that is 8. So these are the 4 individual waiting times for the processes. Now for the average waiting time, we had all these 4 numbers, 4 plus 15 plus 0 plus 8 divided by 4, and this is what we get at 6.75 milliseconds. So this is how we calculate the average waiting time. Now let us come to average turnaround time. We use the same Gantt chart, okay. So in this Gantt chart, so let us see for P1. Now P1 is here, it ends at 11, so this 11 is the turnaround time. So because in turnaround time we consider the execution time as well as the waiting time, everything. So this ends at 11, so this is 11. Now regarding P2 ends here at 22, but 1 millisecond it arrived late, so we subtract this 1 millisecond from this 22, so we get it is 21. So this was 11, this is 21. Then for P3, it ends at 6, but 2 is the arrival time, so 6 minus 2 is 4, so this is 4. And then for P4 it is 16, but 16 minus 3, because 3 is the arrival time, so we subtract that. So finally turnaround time is 11 plus 21 plus 4 plus 13 divided by 4, that is 12.25 millisecond. So this is the average turnaround time for this particular case. So that's all for this particular session. In the next session we will study the priority scheduling. Thanks for watching.